Welcome to Tuna Theory, the channel where science dives deep, true stories get untangled, inventions spark your imagination, theories to unhook, and weird things will get even weirder, weirder than your neighbor.
Welcome to Tuna Theory. The series on theories today's discussion is the quantum field theory. It get rough, so throw on a field and hang in there. Quantum field theory, or QFT, captures the cosmos at its deepest level. It redefines particles as vibrations in expansive fields, each a derivative of space and time. Picture a vibrant tapestry where electrons, photons, and quarks emerge from these fundamental layers. Quantum field theory, a phrase that evokes both awe and trepidation. It's the language of the universe at its most fundamental level, a tapestry woven from the threads of quantum mechanics and special relativity. But what is it really? To grasp quantum field theory, one must first understand its roots. Imagine a world where particles are not just tiny specks, but excitations in a vast field that permeates all of space and time. This is the essence of QFT. Each particle, whether it be an electron, a photon, or a quark, is merely a manifestation of these underlying fields. But before we delve deeper, let's talk prerequisites. To embark on this journey, you must be familiar with several key equations. The Schrödinger equation, the heart of quantum mechanics, lays the groundwork. Then there's the Lagrangian and Hamiltonian formulations from classical mechanics, guiding us through the dance of particles. And let's not forget the principles of special relativity, which remind us that time and space are intertwined in ways that defy our intuition. Yet, despite its elegance, quantum field theory has a reputation for being daunting. The challenge lies not in the difficulty of its components, but in the sheer number of them. It's a complex web of ideas, each thread essential to the whole. The transition from quantum mechanics to QFT is a shift in perspective, but fear not, the journey is worth it. As we navigate this intricate landscape, we find that the book is structured to guide us step by step. Each concept builds upon the last, creating a logical progression that illuminates the path ahead. We start with the simplest examples, gradually escalating to the profound complexities of the standard model. But what makes this exploration truly rewarding is the realization that we're not just learning a set of equations, we're engaging with the very fabric of reality. We're learning how particles interact, how forces arise, and how the universe behaves at its most fundamental level. Now, if you're reading this on your own, I implore you, find a companion for this journey. Discussing these ideas with another person can deepen your understanding and bring clarity to the fog of confusion. And remember, persistence is key. If you find a section challenging, revisit it. Often the light of understanding shines brightest after several attempts. Yet let's not ignore the limitations of our text. It does not delve into the rigorous proofs that underpin these theories, nor does it explore the connections between QFT and condensed matter physics. This focus on elementary particle physics is intentional, aiming to provide a clear and accessible introduction. In conclusion, as you stand on the brink of this intellectual adventure, remember that quantum field theory is one of humanity's greatest achievements. It offers a precise and accurate description of the natural world, revealing the intricate dance of particles and forces that shape our universe. So let us embark on this journey together, ready to explore the depths of quantum field theory and uncover the mysteries that lie within states, ensuring we account for the various spin configurations of the decay products. The beauty of quantum mechanics shines through as we analyze the contributions to the decay rate, leading us to precise predictions that can be tested against experimental data. As we explore these processes, we uncover the underlying symmetries and conservation laws that govern particle interactions. The Noether current, arising from continuous symmetries, plays a pivotal role in ensuring the conservation of quantities such as charge and momentum. In conclusion, the study of cross-sections and decay rates not only deepens our understanding of particle physics, but also illustrates the profound connections between theoretical predictions and experimental observations. Each calculation, each diagram, brings us one step closer to unraveling the mysteries of the universe. We embark on an exploration of cross-sections and decay rates, pivotal concepts that allow us to quantify the interactions of particles in quantum field theory. Let's begin with a theory involving two real scalar fields, A and B, where the interaction term is L1 is GAB2. Imagine a scenario where the mass of particle, A, exceeds twice that of particle, B, M(A)2 mammated B. This condition is crucial, as it enables particle, A, to decay into two particles of type, B. At tree level, we can compute the total decay rate of particle, A. Using the principles of quantum field theory, the decay rate Gamma serves as a measure of how quickly particle A transforms into two B particles. The calculation is straightforward, leveraging the LSZ reduction formula to connect the scattering amplitude to the decay process. Now let's shift our focus to a different interaction involving a real scalar field, phi, and a complex scalar field, chi, represented by the interaction term L1/GPG chi. Again, we assume that the mass of pi is greater than twice that of chi, m phi 2 me chi. This interaction allows phi to decay into two chi particles, and we can compute the total decay rate for this process in a similar fashion. Next, we delve into Compton scattering, a process where a massless photon scatters off an electron initially at rest. In this fixed target frame, we express the Mandelstam variables S and IU in terms of the initial and final photon energies omega and omega, the scattering angle theta and ft. Between the initial and final photon, momenta can also be articulated in terms of these energies. The differential scattering cross-section, frac to sigma, dE dor d, omega ft, emerges from our calculations, revealing the intricate relationship between the scattering amplitude and measurable outcomes. It's fascinating to see how these results converge to the well-known Klein-Nishina formula, which elegantly describes the scattering of photons by electrons. Now, let's turn our attention to the decay of a moon, represented by the process mu right arrow a nu and nu mu. The decay rate for this process is computed by summing over all possible final states, ensuring we account for the various spin configurations of the decay products. The beauty of quantum mechanics shines through as we analyze the contributions to the decay rate, leading us to precise predictions that can be tested against experimental data. As we explore these processes, we uncover the underlying symmetries and conservation laws that govern particle interactions. The Noether current, arising from continuous symmetries, plays a pivotal role in ensuring the conservation of quantities such as charge and momentum. In conclusion, the study of cross-sections and decay rates not only deepens our understanding of particle physics, but also illustrates the profound connections between theoretical predictions and experimental observations. Each calculation, each diagram, brings us one step closer to unraveling the mysteries of the universe. In quantum field theory, the notion of symmetry plays a pivotal role in understanding the behavior of physical systems. A prime example is the phi-4 theory, which describes a real scalar field, pi, with a Lagrangian given by L, y, frac, 1, 1, 2, z fifa partial, mufi, frac, 1, 2 on zm, m 2 phi 2, frac, 1, 2, 24, z lambda phi, for here, z p chi, z e, and azit, in a lambda, are the renormalization factors that account for the effects of quantum corrections, ensuring that the theory remains predictive at different energy scales. Initially, we consider the case where the mass term, m2s, is positive, leading to a z2s symmetry in the system. The field, phi I, can take on both positive and negative values without altering the physics, represented mathematically as phi-do, phi I. This symmetry is crucial, as it implies that the vacuum state of the theory is stable under this transformation. This condition leads to spontaneous symmetry breaking, where the system favors a non-zero vacuum expectation value for the field, phi. We can shift the field as phi x, yir ho x, plus v, where v har skirt, frac 6, m2 guia lambda, minimizes the potential. This shift introduces a new field, RRHOX, that represents fluctuations around the vacuum state. The consequences of this symmetry breaking are profound. The Lagrangian transforms into a new form that allows us to compute physical quantities such as propagators and vertex corrections. In particular, we are interested in the corrections to the propagator, pi 2, which can be computed using Feynman diagrams. The one-loop correction is given by pi 2, frac lambda, higher 4 pi 2 left, frac 2 epsilon, plus 1 plon left, frac mu 2 m2 right. Right? m2, a k2, bm2.
Love exploring the unexpected? Then don't let this opportunity swim away. Hit subscribe to join the Tuna Theory tribe, give this video a big thumbs up if it reeled you in, and share it with your friends who love a good deep dive into the strange, wild, and wonderful.
Where A and B are the counterterms associated with the renormalization process. The presence of divergences as indicated by the frac1 epsilon just term necessitates the introduction of counterterms to absorb these infinities, allowing us to define a finite theory in the context of the renormalization group. The beta function, beta lambda, fract lambda, del mu x describes how the coupling constant, lambda, changes with the energy scale, mu. For our phi 4 theory, we find that the beta function is positive, indicating that the coupling becomes stronger at higher energies. This behavior suggests the potential for non-perturbative effects and the emergence of new physical phenomena as we probe the theory at different scales. As we delve deeper into the implications of these corrections, we encounter the concept of Goldstone bosons, which arise as a consequence of spontaneous symmetry breaking. The existence of massless modes in the spectrum signals the underlying symmetry of the theory, despite the apparent breaking of that symmetry in the vacuum state. In conclusion, the interplay between broken symmetry and loop corrections in quantum field theory not only enriches our understanding of particle interactions, but also provides a framework for exploring the fundamental nature of forces and fields in the universe. The phi-4 theory serves as a quintessential example of how symmetry principles guide the formulation of physical laws, and the renormalization process ensures their consistency across different energy scales. In the realm of quantum field theory, the exploration of Majorana fields offers profound insights into the nature of particles, particularly in the context of Yukawa interactions. The Lagrangian for a Majorana field, which we denote as psi, encapsulates the dynamics of particles that are their own antiparticles, a characteristic that is especially relevant for neutrinos in certain theoretical frameworks. And the interaction term in our Yukawa theory is elegantly expressed as L1 and frac 1 2 g pi psi frac 1 2 g pi psi, where the Feynman rules derived from this Lagrangian are crucial for calculating scattering amplitudes. In this framework, we must remember that the particles associated with Majorana fields are massive neutrinos, and their interactions can lead to rich phenomenology in particle physics. The vertex factor associated with the interaction is IgC, while the Fermion propagator takes the form frac in I S6 id6 trace. These rules allow us to systematically analyze processes involving Majorana particles. When we consider tree-level processes, such as the scattering of two neutrinos into a scalar particle, we find that the number of incoming and outgoing neutrinos must always be even. This requirement arises from the nature of the Majorana field, where each vertex connects two fermionic lines. Thus, the diagrams we draw must respect this constraint, and we must carefully assign momenta and helicity states to ensure proper conservation laws are upheld. The intricacies of these interactions become apparent as we compute scattering amplitudes. For example, in the process, Nunu Tofi, phi, the amplitude can be expressed as a function of Mandelstam variables, reflecting the underlying symmetries of the process. Notably, the exchange of particles leads to significant implications for the behavior of the amplitude under various transformations, such as crossing symmetry, which allows us to relate different scattering processes to one another. As we delve deeper into the implications of Majorana fields, we encounter the concept of loop corrections, which introduce additional complexity into our calculations. These corrections require us to consider not only the tree-level diagrams but also the contributions from virtual particles that can affect the renormalization of our parameters. The one-loop corrections to the propagators and vertex functions must be computed with care, ensuring that we account for the divergences that arise and properly renormalize our theory. The results of these calculations reveal fascinating features of the theory, including the beta functions that govern the running of the coupling constants. These functions dictate how the interactions evolve with energy, providing a window into the behavior of the theory at different scales. The positivity of the beta function for the Yukawa coupling indicates that the interaction strengthens at higher energies, a hallmark of many theories in particle physics. The study of Majorana fields within Yukawa theory not only enhances our understanding of fundamental particles, but also deepens our appreciation for the symmetries and dynamics that govern their interactions. The Feynman rules we derive serve as a powerful tool for exploring the rich landscape of particle physics, guiding us through the complexities of scattering processes and loop corrections, ultimately illuminating the path toward a more unified understanding of the forces that shape our universe. The profound world of quantum electrodynamics and gauge theories, where the very fabric of our universe is woven with the threads of fundamental interactions. At the heart of this discourse lies the Ward identities, a cornerstone of our understanding of symmetries and conservation laws in quantum field theory. Let us consider the contributions to the scattering amplitude, denoted as T, It is essential to recognize that contributions lacking multivariable poles do not influence the amplitude, such as t. This realization leads us to examine correlation functions, specifically how classical field equations manifest within quantum contexts. The Schwinger-Dyson equations serve as a bridge between classical and quantum realms, illustrating that classical equations of motion hold true within quantum correlation functions, barring certain contact terms. As we navigate through the complexities of quantum electrodynamics involving external photons, we encounter the LSZ formula. This formula elegantly encapsulates the relationship between scattering amplitudes and correlation functions. However, the subtleties of gauge invariance emerge as we replace polarization vectors with four momenta, revealing the profound implications of the Ward-Takahashi identity. This identity asserts that the scattering amplitude vanishes under specific conditions, reinforcing the critical nature of gauge invariance in our theories. Transitioning to non-abelian gauge theories, we confront the challenges posed by anomalies, those pesky deviations that threaten the consistency of our models. The interplay between gauge invariance and anomalies becomes a focal point of our investigation. Anomalies may arise in chiral gauge theories, where the delicate balance of fermionic fields and their transformations under gauge symmetries leads to unexpected divergences. The path integral formulation provides a robust framework for understanding these phenomena. By integrating over all configurations, we uncover the intricate dance of fields and gauge transformations. Yet, as we explore the implications of axial currents and their anomalous divergences, we realize that our theories must grapple with the consequences of these anomalies. The Fujikawa method, a powerful tool, allows us to derive the anomalous behavior of currents directly from the path integral, revealing the underlying structure of gauge theories. As we reflect on the implications of these findings, we recognize the profound significance of Wilson loops in diagnosing confinement in gauge theories. The vacuum expectation value of these loops serves as a litmus test for the presence of confinement, a phenomenon that eludes our understanding in perturbative regimes. The lattice gauge theory emerges as a beacon of hope, offering insights into non-perturbative dynamics and the intricate nature of confinement. The journey through quantum electrodynamics and gauge theories is a testament to the elegance and complexity of our universe. The interplay of symmetries, anomalies, and the profound implications of gauge invariance shapes our understanding of fundamental interactions. As we continue to unravel these mysteries, we stand on the shoulders of giants, forging a path toward deeper insights into the nature of reality itself. We journey into the fascinating realm of electroweak interactions, particularly focusing on hadronic processes. At the core of our exploration is the charged pion decay, a process that elegantly illustrates the interplay between weak interactions and particle physics. We begin with the decay of the charged pion, pi, into a neutral pion, pi0, and a muon, mu, alongside an antineutrino. The decay rate of this process hinges on our understanding of the Fermi coupling constant, GF, which we derive from the muon's decay rate, as discussed in section 88. By analyzing the decay rate of the charged pion, we can determine the crucial parameter, C1 FPI, where FPI represents the pion decay constant. The charged current associated with this weak interaction is represented by the expression J mu I skirt frac 1 2 IC 1 piezo left right arrow partial mupi, which intricately links the decay process to isospin symmetry and the properties of the pion fields. Through experimental comparison, we find that C1 is approximately 0, allowing us to fix the value of the pion decay constant at FPI MESR 924 to TextMev. We shift our focus to neutron decay, right arrow P small bar, nu E. We note that the relevant terms in the charged currents highlight the complexity of weak interactions. The charged current takes the form J mu h frac haufen 2 C 1 pagama mu 1 G a gamma 5 N, where Ga is the axial coupling constant. The effective interaction leads us to an expression for the decay amplitude, T, which encapsulates the dynamics of this process. After a thorough calculation, we arrive at the expression for the decay rate, revealing the intricate relationships between the parameters involved. The neutron decay rate allows us to extract the value of 1 plus 3Ga2 through comparison with experimental data, ultimately yielding Ga 127. Next, we turn our attention to the neutral pion decay into two photons, pi right arrow gamma gamma. Interestingly, our Kirill Lagrangian does not permit a tree-level process for this decay, necessitating a one-loop evaluation. The diagrams involved, particularly those with a proton circulating in the loop, lead us to a decay amplitude that is subject to higher loop corrections. As we analyze the decay amplitude, we uncover the role of the axial current and its anomalous divergence, which plays a pivotal role in our understanding of the electroweak interactions. The interplay between the pion fields and electromagnetic gauge invariance culminates in an expression that captures the essence of this decay process. In conclusion, the electroweak interactions of hadrons, illustrated through processes such as pion decay and neutron decay, reveal a rich tapestry of particle dynamics governed by weak interactions. The intricate relationships between coupling constants, decay rates, and the underlying symmetries of the Standard Model provide profound insights into the fundamental forces that shape our universe. As we continue to unravel these mysteries, we deepen our appreciation for the elegance and complexity inherent in the fabric of particle physics.
Thanks for tuning into Tuna Theory, where the ordinary gets flipped and the extraordinary gets explained. Keep your fins sharp and your minds sharper. Until next time, stay curious and keep exploring the depths.
Mixing notes and a hint of fear.